What if everything we know about the universe, its endless expansion, its vast galaxies, even time itself, was headed towards something unexpected? What if, instead of stretching forever, the universe began to collapse, pulling everything back into a single, unimaginable point? This isn't science fiction. It's a real possibility that physicists have been exploring for decades. The idea of a cosmic crunch, where the universe reverses its expansion and begins to shrink, challenges everything we think we know about space, time, and our place in the cosmos. What would that look like? How would stars, galaxies, and even the fabric of reality respond to such a dramatic shift? And what would it mean for the future of existence itself? In this video, we're diving into the mind-bending theories behind a contracting universe, from the Big Crunch to quantum fluctuations and beyond. Strap in, because we're about to explore one of the most profound mysteries of the cosmos. What happens when the universe decides to turn back on itself? One of the most compelling ideas about the universe's ultimate fate is the Big Crunch theory. Picture this: after billions of years of expansion, the universe's growth begins to slow. Gravity, the relentless force pulling everything together, starts to win the cosmic tug of war against dark energy, the mysterious force driving expansion. Over time, galaxies that once raced away from each other begin to creep closer, stars grow dimmer, and space itself starts to contract. This is the essence of the Big Crunch, a universe that collapses back in on itself, almost like a cosmic rewind. The roots of this theory trace back to Einstein's groundbreaking equations in his theory of general relativity. These equations describe how gravity shapes the fabric of space and time, and they hint at a universe that could either expand forever or eventually collapse, depending on the balance of forces at play. For decades, scientists believed the universe might follow this cyclical pattern: a Big Bang leading to expansion, followed by a contraction and a Big Crunch, potentially setting the stage for another Big Bang. It's a poetic idea, isn't it? A universe that breathes in and out like a living cosmic organism. But how does the Big Crunch contrast with the Big Bang? While the Big Bang describes the explosive beginning of the universe, the Big Crunch imagines its fiery end. In the Big Bang, matter and energy burst outward, creating space and time as we know it. In the Big Crunch, the process reverses. Matter and energy are pulled back together, compressing into an infinitely dense point. This point, often called a singularity, would be eerily similar to the one that birthed the universe in the first place. It's almost as if the universe could be caught in an endless loop of birth, death, and rebirth. Of course, this raises a fascinating question: could the universe truly end as it began? Some scientists argue that a Big Crunch might not be the final chapter, but rather the prelude to another cosmic cycle. Others suggest that the conditions during a collapse could be so extreme that the laws of physics as we know them might break down entirely. What happens to time, space, and even reality itself in such a scenario? These are the kinds of questions that keep physicists up at night, and they remind us just how much we still have to learn about the cosmos. The Big Crunch theory isn't just a scientific idea. It's a window into the profound mysteries of existence. It challenges us to think beyond the boundaries of our current understanding and imagine a universe that's far more dynamic and far more unpredictable than we ever realized. And while the evidence for a Big Crunch remains uncertain, it's a reminder that the story of the universe is still being written, one discovery at a time. But what if the fate of the universe isn't written in stone? What if the key to understanding whether the cosmos will expand forever or collapse lies in something so mysterious that scientists still struggle to define it? Enter dark energy, the elusive force that makes up roughly 68% of the universe and is responsible for its accelerated expansion. This invisible energy, discovered in the late 1990s, is like a cosmic counterweight to gravity. pushing galaxies apart faster and faster. But here's the twist. If dark energy's influence changes over time, it could completely alter the universe's trajectory. Imagine dark energy as a dimmer switch. Right now, it's cranked up high, driving galaxies away from each other at an ever-increasing speed. But what if that switch could be turned down? If dark energy loses strength, gravity, the force that binds stars, galaxies, and even the fabric of space could begin to dominate. Over billions of years, this shift could slow the universe's expansion, stop it entirely, and eventually pull everything back together. This is the scenario that could lead to a big crunch. Scientists have been racing to understand dark energy's behavior. One of the most intriguing questions is whether it's constant or variable. If dark energy weakens over time, the universe's expansion could decelerate, setting the stage for a contraction. But if it remains constant or grows stronger, the universe might continue expanding indefinitely, leading to a very different fate, a heat death, where everything drifts apart into cold, empty darkness. The difference between these two outcomes hinges on the nature of this enigmatic force. Recent observations from telescopes and cosmic surveys are offering tantalizing clues. For example, studies of distant supernova exploding stars used as cosmic mile markers suggest that dark energy's effects might not be uniform across time and space. Some researchers have proposed that dark energy could interact with other components of the universe, like dark matter, in ways we don't yet understand. These interactions could influence whether the universe continues to expand or begins to contract. Yet, despite decades of research, dark energy remains one of the greatest mysteries in modern physics. We don't know what it is, where it comes from, or how it might change in the future. Some theories suggest it could be a property of space itself, while others propose entirely new forms of energy or even modifications to Einstein's theory of gravity. Each possibility holds profound implications for the universe's ultimate fate. What makes dark energy so fascinating is its power to shape the cosmos on the grandest scale. It's not just a theoretical curiosity, it's a force that could determine whether the universe ends in a fiery collapse, a cold fade, or something entirely unexpected. As we continue to probe its secrets, we're reminded that the story of the universe is far from over. Every discovery brings us closer to understanding not just how the cosmos works, but where it's headed. And in that journey, dark energy remains one of the most compelling chapters yet to be written. Gravity, the invisible force that holds planets in orbit, binds galaxies together, and shapes the very fabric of space and time, is at the heart of any discussion about a contracting universe. In a cosmos dominated by expansion, gravity is the counterbalance, the cosmic glue that could one day reverse the tide and bring everything crashing back. But how does this force, which we experience every day as the pull keeping our feet on the ground, operate on the grandest scales imaginable? To understand gravity's role in a contracting universe, we need to look at how it interacts with the largest structures in existence. On the scale of galaxies, gravity is the architect of order. It gathers stars into swirling spirals, pulls clusters of galaxies into vast superclusters, and keeps cosmic structures from flying apart. But in a contracting universe, this same force would take on a far more dramatic role. As gravity begins to overcome the outward push of dark energy, galaxies that once drifted apart would start to converge. Stars and planets, once separated by unimaginable distances, would begin to move closer together, drawn by gravity's relentless pull. Over billions of years, this process would accelerate, compressing the cosmos into an ever-shrinking space. Black holes, those enigmatic regions where gravity is so strong that not even light can escape, would play a particularly fascinating role in this scenario. As galaxies collide and merge, their central supermassive black holes would do the same, creating even more massive gravitational powerhouses. These cosmic behemoths would act like anchors, pulling in nearby matter and energy with increasing intensity as the universe contracts. Over time, these black holes could grow so large and powerful that they dominate entire regions of space, devouring stars, gas, and even other black holes. In the final stages of a cosmic crunch, they might become the last remnants of a collapsing universe, drawing everything into a single, unfathomably dense point. But what about the smaller celestial bodies, stars, planets, and even the atoms that make up everything we know? As gravity tightens its grip, stars would face a dramatic fate. In a contracting universe, the space between stars would shrink, bringing them closer together. This increased density could trigger new star formation in the short term, as clouds of gas and dust are compressed. But as the universe continues to collapse, the intense gravitational forces would overwhelm even the most massive stars, causing them to collapse into black holes or explode in supernova. Planets, too, would be torn apart by the growing gravitational pull, their atoms crushed under the immense pressure. At the quantum level, even the fundamental forces that hold atoms together would be challenged. In the extreme conditions of a contracting universe, gravity could become so strong that it overcomes the electromagnetic force, which binds electrons to atomic nuclei. This could lead to the breakdown of matter itself, as atoms are crushed into a state of unimaginable density. Space and time, as we understand them, might cease to exist in any recognizable form, replaced by a single, infinitely dense point known as a singularity. This is the ultimate destination of a contracting universe, a place where the laws of physics as we know them no longer apply. Yet, even as gravity reigns supreme in this scenario, it's important to remember that our understanding of this force is still evolving. Einstein's theory of general relativity provides a framework for understanding gravity on large scales, but it breaks down at the extremes like those found in a collapsing universe. To fully grasp what happens in such conditions, we may need new theories that unify gravity with quantum mechanics, creating a more complete picture of how the universe works. This is one of the greatest challenges in modern physics, and it's a reminder that the story of gravity and the universe itself is far from finished. Gravity's role in a contracting universe is both awe-inspiring and humbling. It's a force that shapes the cosmos on every scale, from the smallest particles to the largest structures. And while the idea of a universe collapsing under its own weight may seem like a distant possibility, it's a reminder of just how dynamic and unpredictable the cosmos can be. Whether the universe expands forever or contracts into a singularity, gravity will always be at the center of the story, pulling the strings in a cosmic drama that spans billions of years. As the universe contracts, gravity may seem like the undisputed ruler of the cosmos, but there's another player in the game, one that operates on a scale so small it's almost beyond comprehension. Enter quantum mechanics, the science of the very small, where the rules of gravity and relativity give way to a strange, unpredictable world. Even in the face of a cosmic crunch, quantum fluctuations, those tiny, random ripples in spacetime could have a profound impact on how the universe collapses. These fluctuations might not just be a footnote in the story of a contracting universe. They could be the wild card that changes everything. Quantum fluctuations are like the universe's version of static, tiny, unpredictable shifts in energy that happen constantly, even in the vacuum of space. On the grand scale of galaxies and black holes, they might seem insignificant. But as the universe contracts, compressing matter and energy into smaller and smaller regions, these fluctuations could become increasingly important. In a shrinking universe where space itself is collapsing, quantum effects might amplify, creating ripples that could influence the fate of everything around them. One possibility is that quantum fluctuations could give rise to new structures, even as the universe collapses. Imagine a cosmic dance where gravity pulls everything inward, but quantum ripples push back, creating pockets of density and energy that resist the collapse. These pockets could form new stars, galaxies, or even entire regions of space that remain stable while the rest of the universe contracts around them. It's a bit like trying to deflate a balloon with holes. Some areas might collapse while others stubbornly hold their shape. But could quantum physics go even further? Some theories suggest that these fluctuations might not just create new structures. They could potentially prevent a complete collapse altogether. In a scenario known as quantum tunneling, the universe could find a way to escape its own contraction, transitioning into a new state of existence. Think of it as the universe hitting a cosmic reset button, avoiding the singularity and emerging into a new phase of expansion. It's a mind-bending idea, one that challenges our understanding of both quantum mechanics and the ultimate fate of the cosmos. Yet, not all scientists agree on whether quantum effects could truly save the universe from total destruction. Some argue that the sheer scale of gravity during a cosmic crunch would overwhelm any quantum fluctuations, rendering them irrelevant in the face of such immense forces. Others suggest that, while quantum physics might delay the inevitable, it couldn't stop the universe from eventually collapsing into a singularity. The debate is far from settled, and it highlights just how much we still have to learn about the interplay between quantum mechanics and gravity. What makes this idea so fascinating is its potential to rewrite the rules of cosmic destiny. A contracting universe might seem like a one-way trip to oblivion, but quantum mechanics introduces an element of unpredictability, a chance that the cosmos could find a way to survive even in the face of total collapse. It's a reminder that the universe is full of surprises, and that even in its darkest moments there could be a glimmer of hope. As we explore these possibilities, we're reminded that the story of the universe is far from simple. From the smallest quantum ripples to the largest cosmic structures, every piece of the puzzle is interconnected, shaping the fate of everything we know. And while the idea of a cosmic crunch might seem like the end, quantum mechanics offers a tantalizing possibility that even in the face of collapse, the universe might find a way to begin again. It's a story that's still being written, and one that continues to challenge and inspire us as we seek to understand the cosmos and our place within it. What if the universe's fate isn't a dramatic collapse but a slow, cold fade into nothingness? This is the essence of the heat-death theory, a starkly different vision of the cosmos compared to the fiery Big Crunch. While the Big Crunch imagines a universe collapsing in on itself, the heat-death paints a picture of endless expansion where galaxies drift apart, stars burn out, and the cosmos becomes a vast, dark, and lifeless void. These two theories represent opposite ends of the spectrum, one an implosion, the other an eternal drift, and understanding both gives us a fuller picture of the universe's potential futures. The heat-death scenario hinges on the idea that dark energy, the mysterious force driving the universe's accelerated expansion, will continue to dominate. Over trillions of years, galaxies will move so far apart that they become invisible to one another. Stars will exhaust their fuel, leaving behind cold remnants like black holes and neutron stars. Even black holes, the universe's most enduring structures, would eventually evaporate due to a process called Hawking radiation, leaving behind a sea of scattered particles and radiation. The result, a universe so cold, so empty, and so stretched out that no new structures could ever form. It's a chilling thought, a cosmos that doesn't end with a bang but with a whisper. On the other hand, the Big Crunch offers a more dramatic finale. Instead of drifting apart forever, the universe reverses course, pulled back together by gravity's relentless grip. Galaxies collide, stars are torn apart, and everything is compressed into an infinitely dense point. It's a fiery, chaotic end, but one that carries the tantalizing possibility of rebirth. Some theories suggest that a big crunch could lead to another Big Bang, creating a new universe in the ashes of the old. This cyclical model of the cosmos has a poetic symmetry, offering a sense of continuity that the heat-death lacks. So, which scenario is more likely? The answer lies in the balance between gravity and dark energy. Observations of distant supernova and the cosmic microwave background. The faint afterglow of the Big Bang suggests that dark energy is currently winning the cosmic tug-of-war, driving the universe's accelerated expansion. This evidence has led many scientists to favor the heat death as the more probable outcome. However, the nature of dark energy remains one of the greatest mysteries in physics. If its strength changes over time, or if it interacts with other forces in ways we don't yet understand, the balance could shift, potentially paving the way for a big crunch. What makes this debate so fascinating is that it's not just about the universe's fate, it's about the fundamental forces that shape it. The heat death and the big crunch represent two extremes, each governed by a different interplay of energy and gravity. One leads to an eternal, frozen expanse, the other to a fiery collapse and the possibility of renewal. Both challenge us to think beyond our current understanding and grapple with questions that have no easy answers. Ultimately, the universe's fate may depend on factors we've yet to discover. Dark energy's true nature, the behavior of gravity on cosmic scales, and even the role of quantum mechanics could all play a part in determining whether the cosmos ends in a cold fade or a dramatic crunch. As we continue to explore these possibilities, we're reminded that the story of the universe is still unfolding, and that every discovery brings us closer to understanding not just where we're headed, but how we fit into the grand tapestry of existence. Whether the universe ends in a whisper or a roar, one thing is certain: the journey to find out will be as awe-inspiring as the destination itself. If the universe contracts, could time itself reverse? This might sound like the plot of a science fiction movie, but some physicists have seriously considered the possibility that a collapsing universe might cause time to flow backward. The idea hinges on the strange and often counterintuitive nature of time, space, and gravity, especially under extreme conditions. To understand how this could happen, we need to take a closer look at how time behaves in the context of a contracting cosmos. In our everyday experience, time moves in one direction, forward. We remember the past but not the future. Eggs break but never unbreak. This arrow of time, as physicists call it, is deeply tied to the concept of entropy, a measure of disorder in the universe. Entropy always increases over time, which is why things tend to move from order to chaos. But in a contracting universe, the rules might be different. As the cosmos collapses, entropy could decrease and the arrow of time might reverse. Suddenly, the idea of time flowing backward doesn't seem so far-fetched. So, what would a backward-flowing universe look like? Picture this. Instead of stars burning out and galaxies drifting apart, stars would reignite, galaxies would converge, and the universe would grow younger. Events that once unfolded in a specific sequence would play out in reverse. Broken eggs would reassemble, fallen trees would rise, and even memories might unravel as time rewinds. It's a mind-bending scenario, but one that raises fascinating questions about the nature of time itself. Some theories suggest that time reversal could be a natural consequence of the universe's collapse. In the final moments of a cosmic crunch, as matter and energy are compressed into an infinitely dense point, the laws of physics as we know them might break down entirely. In this extreme environment, time could lose its familiar forward direction, becoming a fluid dimension that flows in either direction. This would mean that the distinction between past, present, and future becomes meaningless. a concept that challenges our very understanding of reality. But is this idea supported by science? While the concept of time reversal in a contracting universe is intriguing, it remains highly speculative. One challenge is that our current understanding of time is based on the universe's expansion. The Big Bang set the stage for the arrow of time as we experience it, with entropy increasing and time moving forward. In a contracting universe, the dynamics could be entirely different, but we lack the observational data or complete theoretical framework to say for sure. Some physicists argue that even in a collapsing cosmos, entropy might continue to increase, preserving the arrow of time. Others suggest that quantum mechanics could introduce new rules that prevent time from reversing, even under extreme conditions. What makes this idea so captivating is its implications for our understanding of existence. If time could reverse, would the universe simply retrace its steps, or would it create a new, parallel reality? Could consciousness and memory adapt to a backward-flowing timeline, or would experience itself become fundamentally different? These are questions that push the boundaries of science and philosophy, reminding us just how much we still have to learn about the cosmos. While the idea of time reversal remains a speculative and theoretical possibility, it's a powerful reminder of how much the universe can surprise us. Whether time flows forward, backward, or in some entirely unexpected way, the story of the cosmos is far more complex and far more fascinating than we ever imagined. And as we continue to explore these mysteries, we're reminded that the universe is not just a place of physical laws, but also a canvas for the most profound questions about existence itself. As the universe contracts, the fate of galaxies becomes a dramatic spectacle, a cosmic dance of destruction and transformation. Imagine galaxies, those vast islands of stars, gas, and dust, no longer drifting apart but being pulled together by gravity's relentless grip. Over billions of years, the distances between them would shrink, and the once expansive void of space would become increasingly crowded. Galaxies that were once separated by millions of light years would begin to collide, sparking a chain reaction of cosmic events that would reshape the universe in ways both beautiful and terrifying. When galaxies collide, it's not a sudden, violent crash, but a slow, intricate merging process. Stars within these galaxies are so far apart that they rarely collide directly. Instead, the immense gravitational forces at play cause the galaxies to warp and stretch, pulling streams of stars and gas into long, luminous tails. These interactions can trigger bursts of new star formation, as clouds of gas and dust are compressed, igniting the birth of countless new stars. For a time, the night sky in such a universe might glow brighter than ever, filled with the light of these newborn stars. But this brilliance would be fleeting as the relentless pull of gravity continues to tighten its hold. As galaxies merge, their central supermassive black holes, already millions or even billions of times more massive than our Sun, would begin to orbit each other, spiraling closer and closer. Eventually, these black holes would collide, releasing enormous amounts of energy in the form of gravitational waves. These ripples in spacetime would ripple across the cosmos, a testament to the immense forces at play. The resulting supermassive black hole, now even larger, would dominate its galaxy, consuming stars, gas, and anything else that ventured too close. But what would this mean for the night sky? In the early stages of a contracting universe, the night sky might appear more crowded, with galaxies growing closer and brighter. Over time, however, as galaxies merge and their stars are either consumed by black holes or flung into the void, the sky would grow darker. The once vibrant tapestry of stars and galaxies would fade, replaced by the dim glow of black holes and the remnants of stars. Eventually, even these would be drawn into the growing singularity at the heart of the collapsing cosmos, leaving the night sky an empty, featureless void. This process raises another intriguing question. Could life survive in such a universe? As galaxies collide and stars are destroyed, planetary systems would face increasing instability. Planets might be torn from their orbits, flung into space, or consumed by their own dying stars. Yet, in the midst of this chaos, there might be brief windows of opportunity. In the early stages of galactic collisions, new stars and planets could form, offering the possibility of new life. But as the universe continues to contract, these opportunities would dwindle, leaving little chance for life to persist in the long term. The fate of galaxies in a cosmic crunch is a reminder of the universe's dynamic and ever-changing nature. From the birth of stars in colliding galaxies to the formation of supermassive black holes, the process is both awe-inspiring and humbling. It challenges us to think beyond our own place in the cosmos and consider the broader story of existence, a story that is still unfolding, and one that holds endless mysteries waiting to be discovered. As we gaze at the night sky, we're reminded that the universe is a place of constant change, where even the most familiar sights may one day be transformed beyond recognition. As galaxies collide and stars are consumed in a contracting universe, black holes emerge as the ultimate cosmic powerhouses, these enigmatic regions of space-time where gravity is so intense that nothing, not even light, can escape, become the dominant players in the universe's final act. In a cosmos shrinking under gravity's relentless pull, black holes grow larger and more powerful, devouring everything in their path. What happens when these gravitational giants take center stage? The answer lies in their ability to shape the universe's ultimate fate, transforming the cosmos into a landscape dominated by their overwhelming force. In the early stages of contraction, black holes begin to feast on the chaos around them. As galaxies merge, their central supermassive black holes, already massive beyond comprehension, start to orbit one another, locked in a gravitational dance. Over time, these black holes spiral closer, eventually colliding in cataclysmic events that send ripples through spacetime itself. These collisions release energy on an unimaginable scale, creating gravitational waves that echo across the universe. But this is only the beginning. As the universe continues to shrink, black holes grow even larger, consuming stars, gas, and even other black holes. They become the universe's gravitational anchors, pulling in everything around them with increasing intensity. Imagine a universe where black holes are no longer isolated phenomena but interconnected hubs of destruction. As they merge and grow, they form networks of gravitational power, drawing in matter from all directions. Over billions of years, these networks expand, linking black holes across vast distances. The night sky, once filled with the light of stars and galaxies, would grow darker as more and more matter is consumed. Eventually, the entire cosmos could be dominated by a single, universe-sized black hole, a singularity so massive that it encapsulates everything that ever was. This is the ultimate expression of a cosmic crunch, a universe collapsing into itself, leaving behind a single point of infinite density. But what happens inside such a singularity? The truth is, we don't know. Our current understanding of physics breaks down at the extremes of gravity and density. Einstein's theory of general relativity, which describes gravity on large scales, cannot fully explain what occurs within a singularity. Some theories suggest that the laws of space and time cease to exist, replaced by conditions that defy our understanding of reality. Others propose that a singularity could be a gateway to another universe or a new phase of existence. Whatever the case, the formation of a universe-sized black hole would mark a point of no return, a moment where the cosmos as we know it comes to an end. Yet, even in this seemingly bleak scenario, there are hints of possibility. Some scientists speculate that a singularity could be the birthplace of a new universe, a cosmic reset button that triggers another Big Bang. This idea, known as the Big Bounce, suggests that the universe might follow a cycle of expansion and contraction, with each collapse leading to a new beginning. While this remains speculative, it offers a glimmer of hope, a reminder that even in the face of total destruction, the universe might find a way to begin again. The role of black holes in a contracting universe is both awe-inspiring and humbling. They are the ultimate expression of gravity's power, capable of reshaping the cosmos on the grandest scale. As we explore their potential dominance in a cosmic crunch, we're reminded of just how much we still have to learn about these mysterious objects and the universe they inhabit. Whether they mark the end of existence or the start of something new, black holes remain one of the most fascinating and enigmatic features of the cosmos, challenging us to think beyond the boundaries of our current understanding. As galaxies collide and black holes grow in a contracting universe, there's another invisible force quietly shaping the cosmos: dark matter. This mysterious substance, which makes up about 85% of the universe's total mass, doesn't emit light or energy, but its gravitational influence is undeniable. While dark matter is often thought of as a stabilizing force, holding galaxies together and shaping the large-scale structure of the universe, its role in a collapsing cosmos could be far more dynamic and far more consequential. Dark matter's influence begins on the grandest scales. In an expanding universe, it acts like a cosmic scaffold, providing the gravitational framework that allows galaxies and galaxy clusters to form. But in a contracting universe, its role could shift dramatically. As gravity begins to pull everything back together, dark matter's immense mass would amplify the forces driving the collapse. Imagine dark matter as the unseen hand guiding the universe's contraction, pulling galaxies closer and compressing space itself. The more dark matter there is, the stronger its gravitational pull, and the faster the universe might collapse. But how exactly does dark matter interact with gravity in this scenario? Unlike ordinary matter, which can clump together to form stars, planets, and galaxies, dark matter doesn't interact with light or electromagnetic forces. It's invisible, passing through other matter as if it weren't there. Yet, its gravitational pull is real and measurable. In a contracting universe, this means dark matter wouldn't just influence the collapse, it would dominate it. As galaxies and stars are compressed, dark matter would continue to exert its pull, drawing everything inward with increasing intensity. One intriguing possibility is that dark matter could accelerate the crunch. If dark matter's density increases as the universe contracts, its gravitational influence would grow stronger, speeding up the collapse. This could lead to a faster, more violent contraction than if dark matter weren't present. Some theories even suggest that dark matter could create regions of extreme density, where the pull of gravity becomes so strong that it triggers the formation of new black holes or other dense structures. These regions could act as gravitational anchors, pulling in surrounding matter and accelerating the universe's collapse on a local scale. Yet, there's still so much we don't know about dark matter. Its true nature remains one of the greatest mysteries in physics. Is it made up of particles we haven't yet detected? Does it interact with other forces in ways we can't yet measure? The answers to these questions could have profound implications for how dark matter behaves in a contracting universe. For example, if dark matter particles interact with each other through forces beyond gravity, it could alter the way the universe collapses, potentially creating pockets of stability or even delaying the crunch. What makes dark matter so fascinating is its dual nature. On one hand, it's a stabilizing force shaping the universe as we know it. On the other, it's a wild card capable of accelerating or altering the cosmos's ultimate fate. This duality challenges us to think beyond our current understanding and consider how even the most mysterious components of the universe could play a pivotal role in its final chapter. As we explore the role of dark matter in a contracting universe, we're reminded of just how interconnected the cosmos truly is. From the smallest particles to the largest structures, every piece of the puzzle matters. And while the idea of a cosmic crunch might seem like the end of everything, it's also a reminder that the universe is full of surprises. Whether dark matter accelerates the collapse or introduces new complexities, its presence ensures that the story of the cosmos is far from simple and far from over. What if the universe's collapse wasn't the end, but the beginning of something entirely new? This is the heart of the Big Bounce theory, a fascinating idea that suggests a contracting universe might not result in total destruction. Instead, it could rebound, sparking a new Big Bang and setting the stage for another cosmic cycle. Imagine the universe as a cosmic rubber band stretched to its limit, then snapping back to start all over again. This theory offers a glimmer of hope that the cosmos isn't destined for a single, fiery finale, but could be part of an endless loop of birth, death, and rebirth. At the core of the Big Bounce is a radical reimagining of the universe's fate. Unlike the Big Crunch, where everything collapses into an infinitely dense singularity and ends there, the Big Bounce suggests that the singularity could act as a cosmic reset button. When the universe contracts to its smallest possible size, the immense energy and density might trigger a rebound, causing another Big Bang and initiating a new cycle of expansion. It's a vision of the cosmos that's both cyclical and eternal, offering a sense of continuity that's deeply appealing to many scientists and thinkers. But how could such a rebound be possible? The answer lies in the strange and unpredictable world of quantum mechanics. At the quantum level, the rules of physics as we know them break down and new possibilities emerge. One of these is quantum tunneling, a phenomenon where particles can pass through barriers that would normally be impossible to cross. In the context of the Big Bounce, this could mean that the universe, in its most compressed state, doesn't simply collapse into oblivion but instead tunnels through to a new state of existence. It's as if the universe finds a way to escape its own demise, bouncing back with a burst of energy that sets the stage for a new beginning. The Big Bounce theory also ties into the idea of a singularity, a point of infinite density and temperature where the laws of physics as we know them cease to apply. In a traditional Big Crunch, this singularity marks the end of everything. But in the Big Bounce model, it's more like a cosmic pivot point, a moment of transformation rather than annihilation. Some physicists speculate that the extreme conditions of a singularity could trigger quantum fluctuations so powerful that they reverse the contraction, turning collapse into expansion. It's a bit like squeezing a spring. The harder you push, the stronger the rebound. Yet, the Big Bounce isn't without its challenges. One of the biggest questions is whether the universe could truly bounce back without losing its structure. If all matter and energy are compressed into a singularity, would the new universe that emerges be a carbon copy of the old one or something entirely different? Some theories suggest that each bounce could reset the fundamental constants of the universe, altering the laws of physics and creating a cosmos that's unrecognizable from the one before. Others propose that information from the previous universe could somehow carry over, preserving a thread of continuity across cycles. What makes the Big Bounce so compelling is its blend of science and philosophy. It's a theory that challenges us to think beyond the linear narrative of a single universe and consider the possibility of an eternal, cyclical cosmos. It's also a reminder that the universe is full of surprises and that even in the face of collapse, there could be a way forward. Whether the Big Bounce is proven true or not, it's a powerful idea that invites us to imagine a cosmos that's not just vast and mysterious, but also endlessly creative. As we explore the Big Bounce, we're reminded that the story of the universe is far from over. It's a story that's still being written, one that challenges us to think beyond our current understanding and embrace the unknown. Whether the universe ends in a crunch, a bounce, or something entirely unexpected, one thing is certain: the journey to uncover its secrets will continue to inspire and astonish us for generations to come. As the universe contracts, the fate of stars becomes a poignant reminder of the cosmos's impermanence. These celestial beacons, which have illuminated the universe for billions of years, would face a dramatic and often tragic end. In a collapsing cosmos, the very forces that sustain stars' gravity and nuclear fusion would turn against them, leading to a cascade of cosmic events that would extinguish starlight forever. What would this process look like, and how would it unfold across the universe? In the early stages of contraction, stars would face a paradox. As galaxies draw closer together, the increased density of matter could trigger bursts of new star formation. Clouds of gas and dust compressed by gravity might ignite into brilliant new stars, lighting up the night sky with a final burst of cosmic fireworks. For a brief moment, the universe could glow brighter than it has in billions of years, a fleeting celebration of starlight before the inevitable decline. But this burst of life would be short-lived. As the universe continues to shrink, stars would face increasing pressure from the growing gravitational forces around them. Massive stars, which burn through their fuel quickly, would be the first to succumb. These giants, already prone to explosive deaths as supernova, would face an even more dramatic fate. In a contracting universe, the intense gravitational pull could cause them to collapse into black holes long before they exhaust their fuel, cutting their lifespans short. Smaller stars like our Sun might survive longer, but even they wouldn't escape unscathed. As the universe contracts, the space around stars would grow denser, increasing the likelihood of collisions and disruptions. Stars could be torn from their orbits, flung into the void, or consumed by the growing black holes at the centers of galaxies. But what about the light itself? In a contracting universe, the night sky would undergo a dramatic transformation. As stars burn out or are consumed, the light they emit would grow dimmer, and the once vibrant tapestry of the cosmos would fade. Over time, the universe would grow darker, with fewer and fewer stars to illuminate the void. The final days of starlight would be a slow, somber process, a gradual dimming of the cosmic stage as the curtain falls on the universe's most enduring actors. For life, this process would be equally grim. Planets orbiting stars would face increasing instability as their suns dim or explode. Habitable zones, the regions around stars where conditions are just right for life, would shrink and disappear, leaving planets either frozen in darkness or scorched by the remnants of dying stars. Any life that survives would face an increasingly hostile environment, with fewer resources and less time to adapt. In the end, even the hardiest organisms would be unable to withstand the relentless pull of gravity and the fading light of the cosmos. Yet, even in this seemingly bleak scenario, there's a strange beauty to the process. The end of stars in a contracting universe is a reminder of the delicate balance that sustains the cosmos. Stars, for all their brilliance, are fleeting in the grand scheme of things. Their lives a brief spark in the vast darkness of space. As we consider their fate, we're reminded of the universe's dynamic and ever-changing nature, a place where even the brightest lights must one day fade, leaving behind a legacy that echoes across the void. The final days of starlight are both a tragedy and a testament to the universe's complexity. They challenge us to think beyond our own existence and consider the broader story of the cosmos, a story that's still unfolding, and one that holds endless mysteries waiting to be discovered. As we gaze at the night sky, we're reminded that even in the face of collapse, the universe's beauty and wonder endure, inviting us to explore, to question, and to marvel at the grand tapestry of existence. As the universe contracts, it's not just galaxies, stars, and black holes that are pulled inward. Space-time itself, the very fabric of reality, begins to shrink and distort. This collapse of space-time would fundamentally alter the rules of physics as we know them, challenging our understanding of everything from the speed of light to the behavior of particles. What happens when the stage on which the universe plays out its drama starts to fold in on itself? The answer lies in the intricate relationship between space, time, and the forces that govern them. At the heart of this transformation is the concept of space-time, a four-dimensional framework that combines the three dimensions of space with the dimension of time. In our everyday experience, space-time is a stable, predictable backdrop, a canvas on which the universe's events unfold. But in a contracting universe, this canvas begins to warp and shrink. Distances between objects, once vast and unchanging, would grow smaller as space itself contracts. Time, too, would be affected, potentially slowing down or even reversing as the universe collapses. The very rules that govern how matter and energy behave could be rewritten in ways that defy our current understanding. One of the most profound effects of shrinking space-time would be on the speed of light. In our universe, light travels at a constant speed of about 299,792 kilometers per second, a fundamental limit that underpins much of modern physics. But in a contracting cosmos, this constant could change. As space-time compresses, the path light travels would shrink, potentially altering how we perceive distance and time. Imagine looking out at the stars and seeing them grow closer, not because they're moving, but because the space between them is collapsing. This distortion could make the universe appear smaller and more crowded, even as the light from distant stars grows dimmer and redder, stretched by the intense gravitational forces at play. The behavior of particles would also be thrown into chaos. In our current universe, particles like electrons and quarks follow predictable patterns, governed by the fundamental forces of nature. But in a contracting universe, these forces could be overwhelmed by the sheer intensity of gravity. Quantum mechanics, which describes the behavior of particles on the smallest scales, might no longer apply in the same way. Particles could be crushed together, merging into new forms of matter or energy. Even the fundamental constants of physics, like the gravitational constant or the charge of an electron, could change, leading to a universe where the laws of physics are unrecognizable. This collapse of space-time raises another intriguing possibility: the breakdown of causality. In our universe, cause and effect are fundamental principles. Events happen in a specific order, and the past influences the future. But in a contracting cosmos, the shrinking of space-time could blur these distinctions. Time itself might no longer flow in a single direction, leading to scenarios where cause and effect are reversed or entangled. Imagine a universe where the future influences the past, or where events unfold in a chaotic, unpredictable sequence. It's a concept that challenges our most basic assumptions about reality. And what about the fabric of space-time itself? Could it tear or rupture under the immense pressure of contraction? Some theories suggest that as space-time shrinks, it could develop rips or singularities, points where the fabric of reality breaks down entirely. These tears could create regions where the laws of physics cease to apply, leading to unpredictable and potentially catastrophic consequences. In such a scenario, the universe might not collapse into a single point but fragment into disconnected regions, each with its own set of physical laws. The collapse of space-time is a reminder of just how interconnected the universe truly is. From the largest galaxies to the smallest particles, everything is shaped by the fabric of space and time. As we explore how this fabric might change in a contracting universe, we're reminded of the fragility of the cosmic stage on which we all play our part. It's a story that challenges us to think beyond our current understanding and grapple with questions that have no easy answers. Whether space-time collapses into a single point, fragments into chaos, or transforms into something entirely new, one thing is certain: the universe will continue to surprise us right up to the very end. As the universe contracts, one of the most fascinating questions revolves around entropy, the measure of disorder in the cosmos. In an expanding universe, entropy always increases, driving the familiar flow of time from order to chaos. Broken eggs don't reassemble, stars burn out rather than reignite. But in a contracting universe, this fundamental rule could be turned on its head. If entropy decreases as the universe shrinks, what does that mean for the arrow of time and for the fate of everything within the cosmos? To understand entropy's role in a cosmic crunch, let's start with how it works in our current expanding universe. Entropy is often described as a measure of disorder, but it's more accurate to think of it as a measure of possibilities. A system with high entropy has more ways to arrange its components, making it more disordered. For example, a shattered glass has higher entropy than an intact one because the pieces can be arranged in countless ways. In the universe, entropy increases as energy spreads out and matter becomes more evenly distributed. Stars burn fuel, galaxies drift apart, and the cosmos grows more disordered over time. This increase in entropy is why time has a direction, why we remember the past but not the future. But in a contracting universe, the story could be very different. As gravity pulls everything back together, matter and energy would become more concentrated, reducing the number of possible arrangements. Imagine a box filled with marbles. When the box is large, the marbles can move freely, creating many possible configurations. But if the box shrinks, the marbles are forced closer together, limiting their movement and reducing the number of possible arrangements. In a similar way, a contracting universe could see entropy decrease as matter and energy are compressed into smaller and smaller regions. This reversal of entropy could have profound consequences, not just for the physical universe, but for the very nature of time itself. If entropy decreases, the arrow of time, the direction in which events unfold, might also reverse. Instead of moving from order to chaos, the universe could move from chaos to order. Broken eggs might reassemble, stars could reignite, and the cosmos might grow younger rather than older. This doesn't mean that time would literally flow backward, but it could mean that the sequence of events we're familiar with, birth, life, and decay, would play out in reverse. It's a mind-bending idea, one that challenges our most basic assumptions about how the universe works. But could entropy truly decrease in a contracting universe? The answer depends on the balance of forces at play. While gravity pulls matter together, increasing order, other factors like quantum fluctuations and the behavior of dark energy could complicate the picture. Some theories suggest that even in a contracting cosmos, entropy might continue to increase in localized regions, creating pockets of disorder within an overall trend toward order. Others propose that the laws of thermodynamics, the rules governing entropy, might break down entirely under the extreme conditions of a cosmic crunch, leading to unpredictable outcomes. What makes this idea so compelling is its implications for the universe's ultimate fate. If entropy decreases, the cosmos might not end in a chaotic, disordered state, but instead in one of increasing order and simplicity. This could mean that the universe's final moments are not a fiery collapse or a cold fade, but a transformation into something entirely new, a state of existence that defies our current understanding. It's a reminder that the story of the universe is far from simple, and that even the most fundamental laws of physics might be rewritten in the face of extreme conditions. As we explore the role of entropy in a cosmic crunch, we're reminded of just how interconnected the universe truly is. From the smallest particles to the largest structures, every piece of the puzzle is shaped by the balance of order and disorder. And while the idea of a contracting universe might seem like the end of everything, It's also a reminder that the cosmos is full of surprises, a place where even the most familiar rules can be turned upside down, inviting us to rethink what we know about time, space, and the nature of existence itself. The final moments of a contracting universe would be nothing short of apocalyptic, a cosmic crescendo of gravity's ultimate triumph. As the universe nears its end, the relentless pull of gravity would reach its peak, compressing matter and energy into an ever-shrinking space. Galaxies, stars, and even black holes would be drawn together in a cataclysmic convergence, leading to a series of dramatic and irreversible events. But what exactly would this look like? Let's journey into the universe's final act, where the very fabric of reality is stretched to its limits. As the universe contracts, the first visible sign of its impending doom would be the collision and merging of supermassive black holes. These gravitational giants, already millions or even billions of times more massive than our Sun, would begin to orbit one another, spiraling closer and closer until they collide. When two black holes merge, they release an enormous burst of energy in the form of gravitational waves, ripples in the fabric of spacetime that echo across the cosmos. In the final stages of contraction, these mergers would become more frequent and violent, each one sending shock waves through the shrinking universe. The night sky, already dimmed by the fading light of stars, would be punctuated by these invisible but powerful events, a silent testament to the universe's collapse. But the merging of black holes is just the beginning. As the universe continues to shrink, the density of matter would increase exponentially. Stars, planets, and even the atoms that make up everything we know would be crushed under the immense pressure. The very fabric of space itself would warp and distort, compressing distances and altering the flow of time. In this extreme environment, even the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces might begin to behave in unpredictable ways. The laws of physics as we understand them could break down entirely, leaving us with no framework to predict what comes next. At the heart of this chaos lies the singularity, a point of infinite density and zero volume where all the universe's matter and energy are compressed. This is the ultimate destination of a contracting universe, a place where gravity's pull becomes so strong that nothing can escape it. Singularities are already mysterious enough on their own. They exist at the centers of black holes, where our understanding of physics fails. But in the final moments of a cosmic crunch, the entire universe could collapse into a single, all-encompassing singularity. Imagine the entire cosmos, every star, every galaxy, every particle of matter, squeezed into a point smaller than the tip of a pin. It's a concept that defies imagination, yet it's a real possibility in the face of a contracting universe. What happens inside a singularity? The truth is, we don't know. Our current theories of physics, including Einstein's theory of general relativity, break down at the extremes of density and gravity. Some scientists speculate that a singularity could be a gateway to another universe or a new phase of existence. Others suggest that it might mark the true end of everything, a point beyond which nothing can exist. What we do know is that a singularity represents a boundary, a place where the rules of the universe as we know them cease to apply. It's a reminder of just how much we still have to learn about the cosmos and its ultimate fate. Yet, even in the face of this seemingly inevitable collapse, there are intriguing possibilities. Some theories propose that the singularity might not be the end but a new beginning. The immense energy and density of a singularity could trigger a rebound, sparking another Big Bang and setting the stage for a new universe. This idea, known as the Big Bounce, suggests that the universe might follow a cyclical pattern of expansion and contraction, with each collapse leading to a new beginning. It's a vision of the cosmos that's both poetic and hopeful, offering a sense of continuity in the face of destruction. The final moments of a contracting universe are a reminder of the fragility and complexity of existence. From the merging of black holes to the formation of a singularity, every step in this process challenges our understanding of reality. It's a story that's both awe-inspiring and humbling, inviting us to think beyond the boundaries of our current knowledge and imagine a universe that's far more dynamic and far more mysterious than we ever realized. Whether the cosmos ends in a singularity, a rebound, or something entirely unexpected, one thing is certain: the journey to uncover its secrets will continue to inspire and astonish us for generations to come. What if our universe isn't alone? What if, as it contracts into a cosmic crunch, there are countless other universes out there, each with its own story and fate? This is the realm of the multiverse, a mind-bending idea that suggests our universe is just one of many, perhaps infinite, universes coexisting in a vast cosmic tapestry. But if our universe begins to collapse, what happens to the others? Could a contracting universe drag its neighbors down with it, or would the multiverse remain untouched, a sprawling network of realities unaffected by the end of just one? The concept of the multiverse isn't just science fiction. It's a serious scientific idea with roots in theories like string theory, quantum mechanics, and cosmic inflation. According to these theories, other universes might exist alongside ours, separated by dimensions we can't perceive or tucked away in pockets of space-time we'll never reach. Some universes might have different physical laws, different constants, or even different numbers of dimensions. Others could be eerily similar to ours, almost like cosmic twins. But the question remains, if our universe contracts, does it interact with these other realities, or are they entirely disconnected? One possibility is that a contracting universe could create ripples across the multiverse. Imagine our universe as a bubble in a vast cosmic foam. When one bubble pops, or in this case, collapses, it could send shockwaves through the surrounding foam, affecting nearby universes. These interactions might be subtle, like a gentle nudge that alters the trajectory of another universe's expansion. Or they could be more dramatic, triggering collapses or expansions in neighboring realities. It's a bit like tossing a pebble into a pond. The ripples spread outward, touching everything in their path. But in this case, the pond is the multiverse, and the ripples are cosmic forces we can barely comprehend. On the other hand, some theories suggest that universes in the multiverse are entirely isolated from one another, like separate rooms in an infinite mansion. If this is the case, a contracting universe might have no effect on its neighbors at all. Our universe could collapse into a singularity, disappearing from existence, while the multiverse continues on, unaffected. This idea raises another intriguing question. Could a collapsing universe create new universes in its wake? Some theories propose that a singularity formed during a cosmic crunch could act as a seed for a new Big Bang, birthing a fresh universe in the multiverse's ever-expanding network. It's a cosmic cycle of death and rebirth, where the end of one universe becomes the beginning of another. But how would we ever know? The challenge with studying the multiverse is that, by definition, it exists beyond the boundaries of our observable universe. We can't see these other realities, measure their effects, or even confirm their existence. Yet, the idea of a multiverse offers a fascinating framework for understanding the ultimate fate of our own universe. If the multiverse is real, then the collapse of our universe might not be the end of everything, just the end of our chapter in a much larger story. The multiverse also introduces the possibility of cosmic diversity. While our universe contracts, others might continue to expand, thrive, or even experience their own unique fates. Some could be expanding forever, others could be collapsing, and still others might exist in a state of balance, neither growing nor shrinking. This diversity adds another layer of complexity to the story of the cosmos. reminding us that our universe's fate might be just one of countless possibilities. As we explore the interplay between a contracting universe and the multiverse, we're reminded of just how much we still have to learn. The multiverse is a concept that pushes the boundaries of science and imagination, inviting us to think beyond the limits of our own reality. Whether the multiverse survives the collapse of our universe or remains untouched, it's a reminder that the cosmos is far more vast, mysterious, and interconnected than we ever imagined. And as we continue to probe these mysteries, we're reminded that the story of the universe or universes is still being written, one discovery at a time. Cosmic inflation, the explosive expansion that shaped the early universe, might hold the key to understanding its ultimate fate. This rapid stretching of space, which occurred just fractions of a second after the Big Bang, didn't just create the vast cosmos we see today. It could also have set the stage for a future contraction. But how does an event that happened billions of years ago influence what might happen billions of years from now? The answer lies in the delicate balance between expansion and the forces that could one day reverse it. During the inflationary period, the universe expanded faster than the speed of light, smoothing out irregularities and laying the groundwork for the large-scale structures we observe today. This initial burst of growth left behind a kind of cosmic fingerprint, a specific distribution of matter and energy that continues to shape the universe's evolution. But inflation didn't just set the universe in motion, it also established the conditions for its potential collapse. The same mechanisms that drove rapid expansion could, under the right circumstances, contribute to a future contraction. One way to think about this is to consider inflation as the universe's first act, a dramatic opening scene that set the tone for everything to come. If the universe's expansion slows and reverses, it could be seen as the final act, a cosmic bookend to the story that began with inflation. But what would it take for this reversal to happen? The key lies in the interplay between dark energy, gravity, and the remnants of that early inflationary energy. If dark energy, which currently drives the universe's accelerated expansion, were to weaken over time, gravity could regain the upper hand, pulling everything back together. This tug of war between expansion and contraction is a direct consequence of the universe's initial conditions shaped by inflation. Interestingly, some theories suggest that inflation might not have been a one-time event. In a concept known as eternal inflation, different regions of space could experience ongoing bursts of expansion, creating a multiverse of bubble universes, each with its own unique properties. If our universe is just one of these bubbles, its fate could be influenced by the behavior of neighboring universes. A contracting universe in one bubble might trigger ripples that affect others, or it could remain entirely isolated. This idea adds another layer of complexity to the story, suggesting that inflation's legacy might extend far beyond our own cosmic backyard. But how does this help us predict whether a cosmic crunch is in our future? While inflation provides clues about the universe's early behavior, it doesn't offer a definitive answer. What it does do, however, is highlight the delicate balance of forces that govern the cosmos. By studying the remnants of inflation, such as the cosmic microwave background radiation, scientists can piece together how the universe has evolved and make educated guesses about where it's headed. These observations suggest that while contraction is a possibility, it's far from certain. The universe's fate remains a puzzle, with inflation providing some of the pieces but not the entire picture. What makes cosmic inflation so fascinating is its dual role as both a beginning and a potential end. It's a reminder that the universe's story is deeply interconnected, with each chapter influencing the next. Whether the cosmos continues to expand or eventually contracts, the echoes of inflation will always be there, shaping the universe's journey in ways we're only beginning to understand. As we explore these possibilities, we're reminded that the story of the cosmos is far from over, and that every discovery brings us closer to unraveling its greatest mysteries. What if the end of our universe isn't a solitary event, but a cosmic collision? In the vast expanse of the multiverse, where countless universes may exist alongside ours, the idea of a contracting universe colliding with another isn't just science fiction, it's a tantalizing possibility. Imagine two cosmic bubbles, each containing its own universe, drifting closer and closer until they touch. What happens when these universes collide? Could such an event spark a new Big Bang, resetting the cosmic clock? Let's dive into the fascinating and speculative world of universe collisions and their potential consequences. In a multiverse scenario, universes are often imagined as bubbles floating in an infinite cosmic foam. Each bubble operates under its own set of physical laws, expanding or contracting independently. But what if two bubbles drift too close? Could their boundaries touch, causing the universes within to collide? The short answer is maybe. While the concept is still theoretical, some models suggest that universe collisions could be possible, especially if the multiverse is dynamic and ever-changing. These collisions might not be violent explosions, but rather subtle interactions where the fabric of one universe merges with another. If a collision were to occur, the effects would depend on the nature of the universes involved. For instance, if both universes are expanding, their collision might create a shockwave of energy, rippling through space-time and altering the structure of both realities. Alternatively, if one universe is contracting while the other is expanding, the interaction could be even more dramatic. The contracting universe, already collapsing under gravity's pull, might draw energy or matter from the expanding one, accelerating its collapse or even triggering a rebound. This interplay could lead to a cascade of cosmic events, reshaping the fate of both universes. But could a collision between universes spark a new Big Bang? Some theories propose that the immense energy released during such an event could create the conditions for a new universe to form. Picture this: as two universes collide, their combined energy reaches a critical point, igniting a burst of expansion that births a fresh cosmos. This idea ties into the concept of the Big Bounce, where a contracting universe rebounds into a new phase of expansion. In this case, the collision itself could act as the catalyst, turning the end of one universe into the beginning of another. Of course, the idea of universe collisions raises more questions than answers. How would such an event affect the laws of physics within each universe? Could life survive the collision, or would it be obliterated in the cosmic chaos? And perhaps most intriguingly, could we ever detect evidence of a universe collision? Some scientists have suggested that the cosmic microwave background radiation, the faint afterglow of the Big Bang, might hold clues. Strange patterns or anomalies in this radiation could be the fingerprints of a past collision, offering a glimpse into the multiverse's hidden dynamics. What makes the concept of universe collisions so compelling is its blend of the familiar and the unknown. On one hand, it's rooted in the physics we understand: gravity, energy, and the behavior of space-time. On the other, it pushes the boundaries of our imagination, inviting us to consider realities beyond our own. Whether or not universe collisions are possible, they remind us that the cosmos is a place of endless wonder, where even the most familiar laws of physics can lead to extraordinary possibilities. As we explore these ideas, we're reminded that the story of the universe, or universes, is far from over. It's a story that's still being written, one that challenges us to think beyond the limits of our current understanding and embrace the unknown. Whether the universe ends in a cosmic collision, a fiery crunch, or something entirely unexpected, one thing is certain: the journey to uncover its secrets will continue to inspire and astonish us for generations to come. As the universe contracts, the delicate conditions that allow life to flourish would unravel, leaving behind a cosmos increasingly hostile to existence. Stars, the very engines of life, would be the first to fade. In a shrinking universe, the distances between galaxies and stars would diminish, but this proximity wouldn't bring warmth or light, it would bring chaos. Stars that once burned brightly would collide, explode, or be consumed by growing black holes, extinguishing the light that sustains life. Planets orbiting these stars would face a grim fate, torn from their orbits or scorched by the remnants of dying suns. The once stable environments that nurtured life would vanish, leaving behind a cold, dark void. But the loss of stars is just the beginning. As the universe continues to shrink, planetary systems would face increasing instability. Imagine a solar system where the gravitational pull of nearby stars and black holes becomes stronger, tugging planets out of their stable orbits. Some planets might be flung into the void of space, drifting aimlessly without a star to warm them. Others could be drawn into the gravitational grasp of black holes, crushed under the immense pressure or torn apart by tidal forces. Even Earth, once a haven for life, would face annihilation as the sun grows unstable or is consumed by a black hole. The end of life in a contracting universe wouldn't be sudden. It would be a slow, inexorable decline, marked by the loss of one habitable world after another. For any life that manages to survive, the challenges would only grow more severe. As stars die and planets are destroyed, the resources needed to sustain life would dwindle. Energy sources like sunlight and geothermal heat would become scarce or disappear entirely. The building blocks of life, carbon, oxygen, and water, would be scattered or consumed, making it impossible to rebuild or sustain ecosystems. Even the hardiest organisms capable of surviving in extreme conditions would face insurmountable odds as the universe contracts. In the end, life itself would become a relic of a bygone era, a fleeting spark in the vast darkness of a collapsing cosmos. What would the final days of life in the universe look like? Picture a world where the night sky grows darker with each passing year as stars burn out and galaxies merge. The once vibrant tapestry of the cosmos would fade, leaving behind a cold, empty expanse. For any remaining life, the universe would become a place of isolation and despair, with no hope of escape or renewal. Yet, even in this seemingly bleak scenario, there's a strange beauty to the process. The end of life in a contracting universe is a reminder of the fragility and resilience of existence, a testament to the incredible journey that life has taken from its humble beginnings to its inevitable end. As we consider the fate of life in a contracting universe, we're reminded of just how interconnected the cosmos truly is. From the smallest microbes to the largest galaxies, every piece of the puzzle is shaped by the delicate balance of forces that sustain existence. And while the idea of a universe without life might seem like the ultimate tragedy, it's also a reminder that the story of the cosmos is far from over. Whether life endures in other universes or the seeds of existence are carried forward in some new form, the journey of life is a testament to the universe's endless creativity and wonder. As we gaze at the night sky, we're reminded that even in the face of collapse, the universe's beauty and mystery endure, inviting us to explore, to question, and to marvel at the grand tapestry of existence. As the universe contracts, gravity's overwhelming pull becomes the dominant force, but there's a wild card in this cosmic drama: quantum gravity. This elusive theory, which seeks to bridge the gap between quantum mechanics and general relativity, could completely reshape our understanding of a collapsing cosmos. While Einstein's general relativity explains gravity on large scales, it falters in extreme conditions like those found in a contracting universe. This is where quantum gravity steps in, offering a glimpse into the bizarre and unpredictable behavior of the universe at its smallest and most compressed states. At the heart of quantum gravity is the idea that space and time themselves are quantized, broken into tiny, indivisible units. In our everyday world, space and time seem smooth and continuous, but at the quantum level, they might behave more like a pixelated image with discrete chunks of spacetime. In a contracting universe, as matter and energy are squeezed into smaller and smaller volumes, these quantum effects would become impossible to ignore. The fabric of reality could start to ripple and warp in ways that defy our current understanding, creating conditions where the laws of physics as we know them no longer apply. One of the most intriguing possibilities is that quantum gravity could prevent the universe from collapsing into a singularity altogether. While general relativity predicts an infinitely dense point where gravity becomes infinite, quantum gravity introduces a counterforce that could halt the collapse. Think of it like squeezing a spring. The harder you press, the more resistance you feel. In the same way, quantum effects might create a kind of repulsive force that counteracts gravity's pull, stopping the universe from reaching a singularity. This could mean that the universe doesn't end in a fiery crunch but instead rebounds, leading to a new phase of expansion, a cosmic bounce rather than a collapse. But what would this look like in practice? Imagine the universe shrinking to a point where quantum gravity takes over. Instead of collapsing into a singularity, spacetime might stabilize at a tiny but finite size, like a cosmic seed. From there, the immense energy and density could trigger a new Big Bang, setting off another cycle of expansion. It's a scenario that transforms the end of the universe into a new beginning, offering a glimmer of hope that the cosmos might not end in oblivion but in renewal. Of course, this is still speculative. Quantum gravity remains one of the most challenging frontiers in physics, and we don't yet have a complete theory that unites quantum mechanics and general relativity. However, the implications of such a theory are profound. It could not only change how we view the fate of the universe, but also provide insights into the nature of spacetime, the behavior of black holes, and even the origins of existence itself. What makes quantum gravity so fascinating is its potential to rewrite the rules of the cosmos. It challenges us to think beyond the boundaries of our current understanding and imagine a universe that's far more dynamic and interconnected than we ever realized. Whether it prevents a singularity, triggers a cosmic bounce, or introduces entirely new phenomena, quantum gravity reminds us that the story of the universe is far from finished. As we continue to explore these possibilities, we're reminded that the cosmos is a place of endless wonder, where even the most familiar laws of physics can lead to extraordinary surprises. What if the universe isn't a one-time event but an eternal cycle, endlessly expanding and contracting like a cosmic heartbeat? This is the essence of the cyclic universe theory, a bold idea that challenges our understanding of cosmic beginnings and endings. Instead of a single Big Bang followed by an uncertain fate, the cyclic model proposes that the universe undergoes infinite cycles of birth, death, and rebirth. It's a vision of the cosmos that's both poetic and profound, offering a sense of continuity that stretches across eons. But is there any evidence to support this idea, and could it truly solve the mysteries of the universe's ultimate fate? The concept of a cyclic universe isn't new. Ancient cultures often imagined the cosmos as an eternal cycle, with each ending giving rise to a new beginning. Modern science has given this idea new life, with theories like the Big Bounce suggesting that the universe could rebound from a collapse into a new expansion. At the heart of this idea is the interplay between gravity and quantum mechanics. As the universe contracts, quantum effects could create a repulsive force strong enough to counteract gravity's pull, preventing a total collapse and triggering a new Big Bang. This would mean that the universe doesn't end in a singularity, but instead cycles through phases of expansion and contraction, each one a fresh start. But what evidence do we have for such a cycle? One clue lies in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Some researchers have proposed that subtle patterns or anomalies in this radiation could hint at previous cycles, like echoes of a universe that came before ours. Another piece of the puzzle comes from the behavior of dark energy. If dark energy's strength changes over time, it could create the conditions for a universe that expands, contracts, and rebounds. While these ideas are still speculative, they offer intriguing possibilities for how the cosmos might operate on the grandest scales. The cyclic universe theory also raises fascinating questions about the nature of time and existence. If the universe undergoes endless cycles, does each one resemble the last, or are they entirely different? Could the laws of physics reset with each cycle, creating a cosmos with new rules and constants? Some theories suggest that information from previous cycles might carry over, creating a kind of cosmic memory. Others propose that each cycle is entirely independent, with no connection to the one before. These questions push the boundaries of science and philosophy, inviting us to rethink what we know about the universe and our place within it. What makes the cyclic universe so compelling is its ability to offer answers to some of the deepest mysteries of existence. For example, it provides a potential solution to the problem of entropy. In a single universe model, entropy increases over time, leading to a cold, lifeless end. But in a cyclic universe, entropy could reset with each cycle, allowing for new possibilities and a fresh start. This idea challenges the notion of an irreversible arrow of time, suggesting that the universe might find a way to renew itself generation after generation. Of course, the cyclic universe isn't without its challenges. One of the biggest questions is whether a collapsing universe could truly rebound without losing all structure. Some scientists argue that the extreme conditions of a cosmic crunch would destroy any evidence of previous cycles, making it impossible to confirm whether they occurred. Others point out that our understanding of quantum gravity, the key to a cyclic universe, is still incomplete, leaving many questions unanswered. Despite these uncertainties, the cyclic universe theory offers a captivating vision of the cosmos, one that's both timeless and ever-changing. It invites us to imagine a universe that's not just vast and mysterious, but also endlessly creative, finding new ways to begin again and again. Whether or not the evidence ultimately supports this idea, it's a powerful reminder that the story of the universe is far from over, and that every ending might just be the start of something new. As the universe contracts, even light, something we often take for granted, would undergo dramatic transformations. Light, which travels through space as waves, is deeply tied to the fabric of the cosmos. In an expanding universe, these waves stretch out, shifting toward longer, redder wavelengths, a phenomenon known as redshift. But in a contracting universe, the opposite would happen. As space itself shrinks, light waves would compress, shifting toward shorter, bluer wavelengths in a process called blueshift. This isn't just a subtle change. It's a fundamental shift in how light behaves, and it would have profound consequences for anyone or anything observing the cosmos. Imagine looking up at the night sky in a contracting universe. Over time, the stars and galaxies you see wouldn't just grow closer. Their light would change color, shifting from red to blue as the wavelengths shorten. This shift wouldn't just affect the visible spectrum, it would impact all forms of electromagnetic radiation, from radio waves to X-rays. The energy of light would also increase as wavelengths compress, meaning that what was once harmless starlight could become intense enough to ionize atoms, stripping electrons from their orbits and altering the very structure of matter. In the final stages of contraction, the universe could become a searing sea of high-energy radiation, a far cry from the gentle glow of today's night sky. But what does this mean for observers in a contracting universe? For one, the way we perceive the cosmos would change dramatically. distant galaxies, which currently appear faint and red due to redshift, would grow brighter and bluer as their light compresses. The night sky, once a tapestry of dim, distant points of light, would become a dazzling display of intense, high-energy radiation, yet this brilliance would come at a cost. As light wavelengths shrink and energy increases, the universe would become an increasingly hostile place. High-energy radiation could damage DNA, disrupt ecosystems, and make life as we know it unsustainable. Even if life managed to adapt to these extreme conditions, the universe's contraction would eventually render it uninhabitable. The collapse of light also raises intriguing questions about the nature of observation itself. In an expanding universe, light from distant objects takes time to reach us, allowing us to peer into the past. But in a contracting cosmos, the opposite would be true. As space shrinks, light from distant sources would arrive faster, compressing the timeline of cosmic history. Events that once unfolded over billions of years might appear to happen in rapid succession, like a cosmic time lapse. This compression of time and space would challenge our understanding of causality, making it difficult to distinguish past from present or predict future events. What's perhaps most fascinating is how the collapse of light ties into the broader story of the universe's contraction. Light isn't just a passive observer of cosmic events, it's an active participant, shaped by the very forces that drive the universe's evolution. As gravity pulls everything inward, compressing space and time, light becomes a barometer of the cosmos's changing state. Its shifting wavelengths and increasing energy serve as a warning, signaling the universe's inexorable march toward its ultimate fate. The collapse of light reminds us that even the most fundamental aspects of the cosmos are shaped by its dynamic nature. From the gentle glow of distant stars to the searing radiation of a contracting universe, light tells the story of a cosmos in flux. As we explore these transformations, we're reminded that the universe is far more than a static backdrop. It's a living, breathing entity, constantly reshaping itself and the forces that define it. And in this ever-changing tapestry, light remains both a witness and a participant, illuminating the mysteries of existence until the very end. As the universe contracts, even the tiniest particles could have a profound impact on its fate. Enter neutrinos, ghostly, nearly massless particles that zip through the cosmos, barely interacting with matter. These elusive particles, often overlooked, might hold surprising clues about how a collapsing universe behaves. While they're famously hard to detect, their role in a cosmic crunch could be anything but subtle. Neutrinos are everywhere. Trillions of them pass through your body every second, yet they rarely leave a trace. Born in the hearts of stars, supernova, and even the Big Bang itself, these particles are a fundamental part of the universe's fabric. But in a contracting cosmos, their behavior could change dramatically. As gravity pulls everything closer together, neutrinos, which usually fly through space almost unimpeded, might find themselves more tightly packed, increasing their interactions with other matter and energy. This shift could turn them from passive bystanders into active players in the universe's collapse. One intriguing possibility is that neutrinos could help slow the contraction. In an expanding universe, neutrinos contribute to the overall energy density, but their impact is minimal due to their low mass and weak interactions. However, as the universe contracts, the density of neutrinos would increase, potentially creating a kind of cosmic pressure that counteracts gravity's pull. Think of it like trying to squeeze a balloon filled with air. The more you compress it, the harder it pushes back. Neutrinos, in this scenario, could act as a subtle but significant force, resisting the collapse and perhaps even delaying the universe's final moments. But neutrinos could also play another, more mysterious role. One of the biggest puzzles in physics is the nature of dark matter, the invisible substance that makes up most of the universe's mass. While neutrinos are too light to account for dark matter on their own, some theories suggest that heavier, hypothetical cousins of neutrinos, known as sterile neutrinos, could be the missing piece. If these particles exist, they might interact more strongly with gravity, influencing the collapse in ways we can't yet predict. Their presence could alter the balance of forces in a contracting universe, potentially leading to unexpected outcomes like pockets of stability or even localized rebound. Yet, neutrinos might also serve as cosmic messengers, offering clues about the universe's ultimate fate. In a collapsing cosmos, the density and energy of particles would reach extreme levels, creating conditions similar to those in the early universe. Neutrinos, which were abundant in the moments after the Big Bang, could provide a window into this high-energy environment. By studying how neutrinos behave under such extreme conditions, scientists might gain insights into the fundamental laws of physics, laws that could determine whether the universe ends in a fiery crunch, a cold fade, or something entirely different. What makes neutrinos so fascinating is their dual nature. They're both everywhere and nowhere, interacting so weakly with matter that they're nearly invisible, yet potentially holding the key to some of the universe's deepest mysteries. In a contracting universe, their role could range from subtle resistance to dramatic influence, shaping the cosmos in ways we're only beginning to understand. Whether they slow the collapse, reveal hidden forces, or simply drift through the chaos unchanged, neutrinos remind us that even the smallest particles can have a big impact on the grandest scales. As we explore the role of neutrinos in a cosmic crunch, we're reminded of just how interconnected the universe truly is. From the smallest particles to the largest structures, every piece of the puzzle matters. And while the idea of a contracting universe might seem like the end of everything, it's also a reminder that the cosmos is full of surprises. Whether neutrinos act as cosmic breaks, dark matter candidates, or silent witnesses to the universe's final act, their story is a testament to the endless complexity and wonder of existence. The cosmic web, a vast, intricate network of galaxies, clusters, and filaments spanning the universe, is one of the most awe-inspiring structures in existence. Picture it as a colossal spiderweb with galaxies strung along delicate threads of dark matter, intersecting at massive nodes where galaxy clusters reside. This web has taken billions of years to form, shaped by gravity and the subtle tug of dark energy. But in a contracting universe, this grand architecture wouldn't just crumble, it would unravel in a dramatic and chaotic finale. As the universe begins to contract, the first signs of the cosmic web's collapse would appear in the vast voids between filaments. These empty regions, which make up most of the universe's volume, would shrink faster than the denser filaments and clusters. The once expansive voids would be squeezed, their emptiness filled by the encroaching walls of matter. Galaxies that were once separated by unfathomable distances would start to move closer together, drawn by gravity's relentless pull. Over time, the delicate balance of the cosmic web would be disrupted as filaments stretch, twist, and eventually snap under the pressure. Galaxies themselves would face a turbulent fate. In the early stages of contraction, the increased density of matter could trigger bursts of star formation as gas clouds are compressed and ignited. But this brief resurgence of cosmic activity would be short-lived. As the universe continues to shrink, galaxies would collide and merge at an accelerating rate. Picture two spiral galaxies, each with billions of stars, spiraling toward each other in a slow-motion dance. Their collision would send shockwaves through the surrounding space, triggering bursts of new star formation and the birth of supermassive black holes. Over time, these mergers would become more frequent, creating ever larger galaxies and black holes that dominate their regions of space. The filaments of the cosmic web, the threads that connect galaxy clusters, would also face destruction. In an expanding universe, these filaments act like highways, channeling matter and energy across vast distances. But in a contracting cosmos, they would become tangled and compressed, losing their structure as gravity pulls everything inward. Clusters of galaxies, once held in place by the tension of these filaments, would merge into superclusters, creating dense knots of matter that radiate immense gravitational power. As the collapse progresses, the universe would become a crowded, chaotic place. Galaxies that once drifted peacefully through the void would be pulled into violent collisions, their stars and planets flung into chaos. Black holes, already lurking at the centers of galaxies, would grow even larger as they consume nearby matter. Over time, these black holes would themselves merge, creating gravitational behemoths that dominate entire regions of space. The final stages of the cosmic web's collapse would be both beautiful and terrifying. The once majestic structure, with its delicate filaments and sprawling voids, would be reduced to a dense, swirling mass of matter and energy. The night sky, once filled with the light of countless stars and galaxies, would grow darker as matter is consumed or compressed into black holes. Eventually, the entire cosmic web would collapse into a single, unfathomably dense point, a singularity where the laws of physics as we know them cease to apply. Yet, even in this seemingly bleak scenario, there's a strange sense of symmetry. The cosmic web, born from the seeds of the Big Bang, would return to its origins, compressed into a state not unlike the one from which it emerged. It's a reminder that the universe, for all its complexity and grandeur, is governed by the same forces that shaped its beginnings. Whether the cosmic web's collapse marks the end of everything or the prelude to a new beginning, its unraveling is a testament to the dynamic and ever-changing nature of the cosmos. As we explore the fate of the cosmic web, we're reminded of just how interconnected the universe truly is. From the tiniest particles to the largest structures, every piece of the puzzle is shaped by the forces that govern existence. And while the idea of a collapsing cosmos might seem like the ultimate end, it's also a reminder that the story of the universe is far from simple. Whether it ends in a fiery crunch, a cold fade, or something entirely unexpected, the journey to uncover its secrets will continue to inspire and astonish us for generations to come. What if the very fabric of empty space held the key to the universe's fate? This is where vacuum energy comes into play, a mysterious form of energy that permeates the cosmos, even in the absence of matter. Often associated with dark energy, vacuum energy is thought to be responsible for the universe's accelerated expansion. But in a contracting universe, its role could shift dramatically, shaping the cosmos in ways we're only beginning to understand. Let's explore how this invisible force might influence the universe's collapse and what it could mean for the ultimate fate of everything. Vacuum energy is the energy inherent to space itself, a kind of background hum that exists even in a perfect vacuum. In an expanding universe, this energy acts like a repulsive force, pushing galaxies apart and driving the cosmos to grow faster and faster. But in a contracting universe, its behavior could change. As space shrinks, the density of vacuum energy would increase, potentially amplifying its effects. This could mean that vacuum energy, which once drove expansion, might now accelerate the collapse, pulling everything inward with even greater force. It's as if the universe's own energy turns against it, hastening its demise. But here's where things get even more intriguing. Some theories suggest that vacuum energy isn't constant. It could evolve over time, changing in strength or even reversing its effects. Imagine vacuum energy as a dimmer switch that can be turned up or down. If this energy weakens as the universe contracts, its influence might diminish, allowing gravity to take full control. On the other hand, if vacuum energy grows stronger, it could create a kind of cosmic tug of war with gravity, reshaping the collapse in unexpected ways. This variability introduces a layer of unpredictability. making the universe's fate even harder to pin down. Another fascinating possibility is that vacuum energy could interact with other forces in the universe, like dark matter or quantum fluctuations. These interactions might create pockets of stability or instability, altering the pace and nature of the collapse. For example, if vacuum energy interacts with dark matter, it could create regions where the collapse slows or even halts temporarily, delaying the universe's final moments. These pockets could act like cosmic oases, preserving fragments of the universe's structure even as the rest of it collapses into chaos. What makes vacuum energy so compelling is its dual nature. On one hand, it's a force that drives expansion, shaping the universe on the grandest scales. On the other, it's a wild card, capable of accelerating or altering the collapse in ways we can't yet predict. This duality challenges us to think beyond our current understanding and consider how even the most subtle forces can have profound effects on the cosmos. As we explore the role of vacuum energy in a contracting universe, we're reminded of just how interconnected the cosmos truly is. From the smallest particles to the largest structures, every piece of the puzzle is shaped by the delicate balance of forces that sustain existence. And while the idea of a cosmic crunch might seem like the ultimate end, it's also a reminder that the universe is full of surprises. Whether vacuum energy hastens the collapse, creates pockets of stability, or introduces entirely new phenomena, its story is a testament to the endless complexity and wonder of existence. As we continue to probe these mysteries, we're reminded that the story of the universe is still being written, one discovery at a time. As the universe contracts, one of the most mind-bending questions emerges: what happens to time itself? We often think of time as a constant and unchanging backdrop against which the universe's events unfold. But in a collapsing cosmos, time could behave in ways that defy our everyday experience. From the slowing of clocks to the potential end of time altogether, the collapse of time is a concept that challenges not only our understanding of physics, but also our very perception of existence. In our current, expanding universe, time flows in one direction forward. This arrow of time is deeply tied to the concept of entropy, the measure of disorder in the cosmos. As entropy increases, time moves forward and events unfold in a specific sequence. But in a contracting universe, entropy could decrease, potentially reversing the arrow of time. Imagine a clock ticking backward, stars reigniting, or even memories unraveling as the universe rewinds. It's a scenario that feels more like science fiction than science, but it's rooted in the strange and counterintuitive laws of physics. One way to think about this is to consider how gravity affects time. According to Einstein's theory of general relativity, time slows down in the presence of strong gravitational fields. In a contracting universe, as gravity's pull intensifies, time could slow to a crawl. Clocks on Earth, for example, would tick more slowly compared to those in a less dense region of space. But as the collapse progresses, this effect would become more extreme. In the final moments of the universe, as matter and energy are compressed into an infinitely dense singularity, time could come to a complete halt. It's as if the universe hits the cosmic pause button, freezing everything in place. But what does it mean for time to stop? In our everyday experience, time is the framework that allows us to measure change. The ticking of a clock, the aging of a star, the evolution of life. Without time, there is no change, no progression, no sequence of events. The universe would become a static, timeless state, frozen in a single, unchanging moment. This idea challenges our most fundamental assumptions about reality, suggesting that the flow of time isn't an inherent feature of the cosmos, but a product of its expansion and the increase of entropy. Some theories take this idea even further, proposing that time itself could reverse in a contracting universe. Instead of moving forward, the sequence of events would play out in reverse with effects preceding their causes. Broken eggs would reassemble, stars would reignite, and even the memories of living beings might unravel as time flows backward. While this remains speculative, it's a fascinating possibility that pushes the boundaries of our understanding of time and causality. The collapse of time also raises profound questions about the nature of existence. If time runs out or reverses, what happens to consciousness, memory, and the very fabric of reality? Could life adapt to a backward-flowing timeline, or would experience itself become fundamentally different? These are questions that blur the line between science and philosophy, inviting us to rethink what it means to exist in a universe where time is no longer a constant. What makes the collapse of time so compelling is its ability to challenge our most basic assumptions about the universe. It's a reminder that the cosmos is far more dynamic and unpredictable than we often assume, and that even the most familiar concepts like time can be reshaped by the forces that govern existence. Whether time slows, stops, or reverses in a contracting universe, its story is a testament to the endless complexity and wonder of the cosmos. As we explore these ideas, we're reminded that the story of the universe is still being written. From the ticking of a clock to the ultimate fate of time itself, every discovery brings us closer to understanding not just how the universe works, but how we fit into its grand tapestry. Whether time ends in a frozen singularity, a cosmic rewind, or something entirely unexpected, the journey to uncover its secrets will continue to inspire and astonish us for generations to come. As the universe contracts, another enigmatic player could enter the cosmic stage, cosmic strings. These hypothetical one-dimensional defects in the fabric of space-time are thought to have formed in the early universe during a phase transition much like water freezing into ice. While they remain theoretical, cosmic strings are fascinating not just for their origins but for the potential influence they could have on the universe's collapse. Imagine them as ultra-thin, incredibly dense filaments stretching across the cosmos like cracks in a frozen lake, carrying immense energy and gravitational power. But what role could these cosmic strings play as the universe begins to shrink? In a contracting universe, cosmic strings might act as cosmic anchors, their immense gravitational pull influencing the movement of matter and energy around them. Picture a massive galaxy cluster being drawn toward a cosmic string, its path bending and twisting as it's pulled in. These strings could create regions of extreme density where matter accumulates faster than in other parts of the universe. Over time, these dense regions might collapse into black holes or other massive structures, accelerating the overall contraction. In this way, cosmic strings could act as gravitational hotspots, shaping the universe's collapse in ways that are both dramatic and unpredictable. But cosmic strings aren't just passive participants, they could also leave behind observable traces. As the universe contracts, the intense gravitational fields around cosmic strings might produce gravitational waves, ripples in space-time that could be detected by advanced instruments. These waves would carry unique signatures, offering a potential way to confirm the existence of cosmic strings. Additionally, the interactions between cosmic strings and other structures, like galaxies or black holes, could create bursts of energy or even distortions in the cosmic microwave background radiation, the afterglow of the Big Bang. These traces, if detected, would provide a window into the early universe and the forces that shaped it. The potential influence of cosmic strings also raises intriguing questions about the nature of space-time itself. If these one-dimensional defects exist, they would represent a kind of scar in the fabric of reality, a remnant of the universe's earliest moments. In a contracting universe, these scars could become more pronounced, their gravitational effects magnified as space-time itself is compressed. This could lead to phenomena like cosmic string loops, closed loops of space-time that vibrate and release energy as they interact with the surrounding universe. These loops could act as cosmic lighthouses, emitting bursts of radiation or gravitational waves that signal their presence. Of course, the existence of cosmic strings is still theoretical, and their role in a contracting universe remains speculative. But their potential impact is a reminder of just how complex and interconnected the cosmos truly is. From the tiniest particles to the largest structures, every piece of the puzzle matters, shaping the universe's ultimate fate. Whether cosmic strings accelerate the collapse, leave behind observable traces, or simply drift through the chaos unchanged, their story is a testament to the endless creativity and mystery of the cosmos. As we explore these possibilities, we're reminded that the universe is a place of infinite wonder, where even the most speculative ideas can lead to profound insights. Cosmic strings, with their strange and otherworldly properties, challenge us to think beyond the boundaries of our current understanding and imagine a universe that's far more dynamic and interconnected than we ever realized. Whether they are confirmed or remain a tantalizing possibility, their story is a reminder that the journey to uncover the secrets of the cosmos is far from over, and that every discovery brings us closer to understanding not just how the universe works, but how we fit into its grand tapestry. Now let's zoom way into the very fabric of space-time itself. At the smallest scales, far smaller than an atom, space isn't smooth and calm. Instead, it's a seething, bubbling sea of energy known as the quantum foam. This isn't just poetic language, it's a real phenomenon predicted by quantum mechanics, where space-time is constantly fluctuating, with tiny virtual particles popping in and out of existence. But what happens to this chaotic, microscopic landscape when the universe begins to contract? Could the collapse of the cosmos reshape the quantum foam, and in turn, the very foundation of reality? In an expanding universe, the quantum foam is like a turbulent ocean, constantly churning with energy at the smallest scales. These fluctuations are so tiny that they're almost impossible to observe directly, but their effects ripple through the cosmos, influencing everything from the behavior of particles to the structure of space-time itself. However, in a contracting universe, the rules of the game could change dramatically. As space shrinks, the energy density of the quantum foam would increase, amplifying its chaotic nature. Imagine squeezing a sponge. The tighter you press, the more it resists, and the more its structure changes. In the same way, the quantum foam could become more volatile, its fluctuations growing more intense as the universe contracts. One fascinating possibility is that these amplified fluctuations could create new particles or even entirely new forms of matter. In the extreme conditions of a shrinking universe, the quantum foam might act like a cosmic pressure cooker, forcing particles to interact in ways they never would under normal circumstances. This could lead to the creation of exotic particles or even the breakdown of matter as we know it. For example, protons and neutrons, the building blocks of atoms, could be torn apart by the intense gravitational forces, their quarks and gluons scattering into the quantum foam. It's a scenario where the very structure of matter could unravel, leaving behind a sea of energy and uncertainty. But the quantum foam isn't just a passive observer of the universe's collapse. It could also play an active role in shaping the cosmos's ultimate fate. Some theories suggest that the foam's fluctuations might create regions of instability, where space-time itself begins to warp or tear. These rips in the fabric of reality, known as spacetime singularities, could act as gateways to new dimensions or even new universes. In this way, the quantum foam could be the key to understanding how a contracting universe might transition into something entirely new, rather than simply collapsing into oblivion. What's perhaps most intriguing is how the quantum foam connects the largest scales of the universe to the smallest. While we often think of gravity as the dominant force on cosmic scales at the quantum level, it's just one player in a much more complex dance. As the universe contracts, the interplay between gravity and quantum mechanics could become the defining feature of the cosmos's final act. This interplay might even prevent a total collapse, with quantum effects creating a repulsive force strong enough to counteract gravity's pull. In this scenario, the universe wouldn't end in a singularity but could instead rebound, sparking a new Big Bang and beginning the cycle anew. The collapse of the quantum foam is a reminder that the universe is far more dynamic and interconnected than we often realize. From the smallest particles to the largest structures, every piece of the puzzle is shaped by the forces that govern existence. And while the idea of a contracting universe might seem like the ultimate end, it's also a reminder that the cosmos is full of surprises. Whether the quantum foam accelerates the collapse, creates new forms of matter, or triggers a cosmic rebirth, its story is a testament to the endless complexity and wonder of existence. As we continue to explore these ideas, we're reminded that the universe is a place of infinite possibilities, where even the smallest fluctuations can have profound consequences. What if, as the universe contracts into an inescapable cosmic crunch, there's a hidden escape route, a cosmic shortcut that could transport matter, energy, or even entire civilizations to safety? Enter wormholes, those fascinating theoretical tunnels through space-time that have long captured the imagination of scientists and science fiction fans alike. In a collapsing universe where gravity's pull becomes overwhelming, could wormholes offer a lifeline, a way to sidestep the crushing fate of a cosmic singularity? Let's explore whether these mysterious structures could exist in a contracting cosmos and what their presence might mean for the ultimate fate of everything. Wormholes, also known as Einstein-Rosen bridges, are solutions to Einstein's equations of general relativity. Picture them as shortcuts through the fabric of space-time, connecting two distant points in the universe like a tunnel through a mountain. In theory, they could allow for faster-than-light travel or even provide a passage between different regions of space, time, or even universes. But here's the catch: wormholes are incredibly unstable. Without some form of exotic matter or negative energy to hold them open, they would collapse almost instantly, making them impossible to traverse. In our current expanding universe, wormholes remain a tantalizing but speculative idea. However, in a contracting cosmos, the rules of the game might change. As the universe shrinks, the extreme conditions could create new possibilities for wormholes. One intriguing scenario is that the immense gravitational forces of a cosmic crunch could stabilize these tunnels, at least temporarily. Picture the universe as a crumpling piece of paper. As it folds in on itself, the fabric of space-time might develop natural bridges or tiers, wormholes that could act as escape routes. These tunnels might not last forever, but in the chaos of a collapsing universe, even a fleeting opportunity to escape could be enough to alter the fate of matter, energy, or even life itself. But what would it take to traverse a wormhole in such a scenario? First, the wormhole would need to be large enough and stable enough to allow anything to pass through without being torn apart by tidal forces. Second, it would need to connect to somewhere safe, another region of space, a parallel universe, or even a new cosmic cycle. This raises another fascinating question. Could wormholes link a contracting universe to an expanding one, creating a bridge between the old and the new? Some theories suggest that a wormhole could serve as a kind of cosmic reset button, allowing matter and energy to escape the crunch and emerge in a fresh, expanding universe. It's a poetic idea, offering a glimmer of hope in the face of cosmic doom. Of course, the existence of wormholes in a contracting universe is still highly speculative. Even if they could form, we don't yet know how they would behave under such extreme conditions. Would they remain stable long enough to be useful, or would they collapse under the immense pressure of a cosmic crunch? Could they even be detected, or would they be hidden in the chaos of a collapsing cosmos? These are questions that push the boundaries of our understanding, blending the realms of theoretical physics and imaginative speculation. What makes wormholes so compelling is their potential to rewrite the rules of cosmic destiny. In a universe hurtling toward collapse, they offer a tantalizing possibility of escape or renewal. Whether they're a cosmic lifeline, a bridge to another reality, or simply a fascinating theoretical construct, wormholes remind us that the universe is full of surprises. As we explore these possibilities, we're reminded that the story of the cosmos is far from simple, and that even in the face of collapse, there could be a way forward, a hidden path through the chaos that leads to something new. The idea of wormholes in a contracting universe is more than just a scientific curiosity. It's a reminder of the endless creativity and mystery of the cosmos. Whether they're real or remain a figment of our imagination, wormholes challenge us to think beyond the boundaries of our current understanding and imagine a universe that's far more dynamic and interconnected than we ever realized. As we continue to probe these mysteries, we're reminded that the journey to uncover the secrets of the cosmos is far from over, and that every discovery brings us closer to understanding not just how the universe works, but how we fit into its grand tapestry. As the universe contracts, one of the most fundamental forces holding reality together could face an existential crisis, the Higgs field. This invisible energy field permeates all of space, giving particles their mass and enabling the existence of everything from atoms to galaxies. Without the Higgs field, particles would zip through the cosmos at the speed of light, unable to form the stable structures we rely on. But in a collapsing universe, this field, so vital to the fabric of existence, could destabilize, unraveling the very laws of physics as we know them. What would happen if the Higgs field failed, and how would it reshape the universe's final act? To understand the Higgs field's role, let's break it down. Imagine the universe as a vast ocean with particles swimming through it like fish. The Higgs field is the water, creating resistance that slows particles down and gives them mass. Without this resistance, particles would be weightless, moving freely without forming atoms, molecules, or any of the complex structures that make up the cosmos. In our current expanding universe, the Higgs field is stable, maintaining the delicate balance that allows matter to exist. But in a contracting universe, this stability could be threatened. As space shrinks and gravity's pull intensifies, the energy density of the Higgs field would increase. This heightened energy could push the field toward a tipping point, where it shifts from its current stable state to a new, unstable configuration. Think of it like a ball sitting in a valley. The valley represents the stable Higgs field. But if the ball is pushed over the edge, it rolls into a lower energy state, altering the landscape entirely. In the case of the Higgs field, this shift could have catastrophic consequences, fundamentally changing the properties of particles and the forces that govern them. One immediate effect of a destabilized Higgs field would be the loss of mass for particles. Electrons, quarks, and other fundamental particles would become massless, behaving more like photons, particles of light. Atoms, which rely on the mass of electrons to orbit atomic nuclei, would disintegrate. Molecules built from atoms would dissolve into a chaotic soup of massless particles. The universe, once filled with stars, galaxies, and planets, would transform into a sea of energy, devoid of the structures that make it recognizable. It's a scenario where matter itself ceases to exist in any familiar form. But the collapse of the Higgs field wouldn't just affect matter, it could also rewrite the laws of physics. The Standard Model, our current framework for understanding particle interactions, is built on the assumption that the Higgs field remains stable. If this field collapses, the rules governing the universe could change dramatically. Forces like electromagnetism and the strong nuclear force, which rely on the properties of particles with mass, might behave unpredictably. Even gravity, the force driving the universe's contraction, could be altered, leading to outcomes we can't yet predict. What makes this idea so fascinating is its potential to transform the universe's final moments. Instead of a fiery collapse into a singularity, the destabilization of the Higgs field could lead to a more subtle but equally dramatic end. The universe might dissolve into a state of pure energy, a cosmic reset where the familiar laws of physics no longer apply. Some theories even suggest that this collapse could trigger a phase transition, creating a new universe with entirely different physical constants and laws. It's a mind-bending possibility, a universe that doesn't end in destruction but in transformation. Yet, the collapse of the Higgs field isn't just a theoretical curiosity, it's a reminder of how fragile the cosmos truly is. The forces and fields that sustain existence are delicately balanced, and even a small shift could unravel everything we know. As we explore these possibilities, we're reminded that the story of the universe is far from over. Whether the Higgs field collapses, triggers a new beginning, or remains stable until the end, its story is a testament to the endless complexity and wonder of the cosmos. And as we continue to probe these mysteries, we're reminded that the journey to uncover the secrets of the universe is as awe-inspiring as the destination itself. Now, let's turn our attention to a theory that could profoundly reshape our understanding of the cosmos: supersymmetry. This elegant idea suggests that every particle we know, electrons, quarks, photons, has a hidden partner, a sort of cosmic twin with unique properties. While supersymmetry remains unproven, it's a cornerstone of many modern physics theories, offering potential solutions to some of the universe's biggest mysteries. But what happens to these elusive partner particles in a contracting universe? Could supersymmetry hold the key to understanding the cosmos's ultimate fate? In our current expanding universe, supersymmetry, often abbreviated as SUSY, is thought to provide a kind of cosmic balance. Each particle's superpartner would have properties that help stabilize the universe, smoothing out the rough edges of quantum mechanics and general relativity. For example, the superpartner of an electron, called a selectron, would have a different spin and mass, but its existence could solve puzzles like the hierarchy problem: why gravity is so much weaker than the other fundamental forces. In a collapsing universe, however, this delicate balance could be disrupted. As space shrinks and energy densities skyrocket, the interactions between particles and their superpartners might change in unexpected ways. One possibility is that supersymmetry could break down entirely during the collapse. Imagine the universe as a finely tuned orchestra, with particles and their superpartners playing in perfect harmony. As the universe contracts, the conditions that allow this harmony to exist might vanish, causing the orchestra to fall out of sync. Superpartners, which are thought to be heavier than their counterparts, might decay or transform into other particles, leaving behind a universe where the symmetry is lost. This breakdown could have profound consequences, altering the behavior of matter and energy in ways we can't yet predict. On the other hand, supersymmetry might also play a protective role in a contracting universe. Some theories suggest that superpartners could act as a kind of cosmic buffer, absorbing excess energy and preventing the collapse from accelerating too quickly. Picture a sponge soaking up water. Superpartners might soak up the intense gravitational forces, slowing the contraction and potentially delaying the universe's final moments. This could create pockets of stability where the laws of physics remain intact even as the rest of the cosmos collapses into chaos. But supersymmetry's influence might not stop there. If superpartners exist, they could also interact with dark matter, the mysterious substance that makes up most of the universe's mass. In a contracting cosmos, these interactions could become more pronounced, shaping the way dark matter behaves and influencing the collapse itself. For example, if superpartners are connected to dark matter particles, their decay or transformation could release energy, altering the balance of forces and potentially triggering new cosmic events. What makes supersymmetry so compelling is its ability to connect the smallest scales of the universe to the largest. It's a theory that bridges the gap between quantum mechanics and cosmology, offering insights into everything from particle physics to the fate of the cosmos. Whether supersymmetry stabilizes the collapse, breaks down entirely, or introduces entirely new phenomena, its role in a contracting universe is a reminder of just how interconnected the cosmos truly is. From the tiniest particles to the largest structures, every piece of the puzzle matters, shaping the universe's ultimate destiny. As we explore these ideas, we're reminded that the story of the universe is far from simple. Supersymmetry, with its elegant balance and hidden partners, challenges us to think beyond the boundaries of our current understanding and imagine a cosmos that's far more dynamic and interconnected than we ever realized. Whether it's the key to solving the universe's greatest mysteries or simply a fascinating theoretical framework, supersymmetry invites us to keep probing the unknown, uncovering the secrets of existence one discovery at a time. As the universe contracts, the very foundations of physics as we know them could begin to crumble. The standard model of particle physics, our most comprehensive framework for understanding the building blocks of the universe, might not survive the extreme conditions of a cosmic crunch. This model, which has withstood decades of experimentation and scrutiny, describes the behavior of particles and forces with astonishing precision. But in a collapsing cosmos where gravity reigns supreme and energy densities reach unimaginable levels, the standard model could face its greatest challenge yet. What happens when the rules we rely on to explain reality no longer apply? At the heart of the standard model are the fundamental particles, quarks, electrons, neutrinos, and their counterparts, as well as the forces that govern their interactions. These forces, electromagnetism, the strong nuclear force, and the weak nuclear force, are mediated by particles like photons, gluons, and W and Z bosons. Together, they create the intricate dance of matter and energy that shapes everything from atoms to galaxies. But in a contracting universe, this dance could descend into chaos. As gravity tightens its grip, the delicate balance between particles and forces might be disrupted, leading to behaviors that the standard model simply can't predict. One of the first casualties of this breakdown could be the stability of matter itself. In our current universe, protons, the building blocks of atomic nuclei, are remarkably stable, with lifespans estimated to be many times the age of the universe. But in a collapsing cosmos, the extreme conditions could destabilize protons, causing them to decay into lighter particles. This process, known as proton decay, would unravel the very fabric of matter, dissolving atoms and molecules into a sea of energy. Without protons, the structures that make up stars, planets, and even life itself would cease to exist. The forces that hold particles together could also falter. The strong nuclear force, which binds quarks into protons and neutrons, might weaken under the immense pressure of a collapsing universe. If this force loses its strength, atomic nuclei could disintegrate, releasing their constituent quarks into the chaos. Similarly, the electromagnetic force, which governs the interactions between charged particles, could become distorted, altering the behavior of atoms and molecules. Electrons, which orbit atomic nuclei, might no longer be bound by the same rules, leading to the breakdown of chemical bonds and the collapse of matter as we know it. Even the Higgs field, which gives particles their mass, could face unprecedented challenges. As the universe contracts, the energy density of the Higgs field might increase to the point where it becomes unstable. If the field collapses into a lower energy state, particles could lose their mass entirely, transforming into massless entities that behave like photons. Without mass, the familiar structures of the universe would dissolve, leaving behind a chaotic soup of energy and radiation. What makes this scenario so fascinating is that it forces us to confront the limits of our understanding. The Standard Model has been remarkably successful in explaining the universe as we know it, but it was never designed to account for the extreme conditions of a cosmic crunch. In the face of such collapse, we may need entirely new frameworks to describe the behavior of particles and forces. Theories like quantum gravity, string theory, or even entirely new paradigms could come to the forefront, reshaping our understanding of reality itself. Yet, the collapse of the Standard Model isn't just a scientific problem, it's a reminder of how much we still have to learn. The universe, for all its complexity, is governed by forces and particles that remain mysterious in the face of extreme conditions. As we explore these possibilities, we're reminded that the story of the cosmos is far from finished. Every discovery, every challenge to our understanding, brings us closer to unraveling the greatest mysteries of existence. And in that journey, the collapse of the Standard Model is not an end, but a new beginning, a call to explore the unknown and redefine what we think we know about the universe. As the universe contracts, pushing matter and energy into smaller and smaller volumes, the very nature of reality could shift in ways that defy our current understanding. Enter string theory, a revolutionary framework that reimagines the building blocks of the universe not as point-like particles, but as tiny, vibrating strings. These strings, each vibrating at different frequencies, could hold the key to understanding the extreme conditions of a collapsing cosmos. But how does this elegant theory, which aims to unify all fundamental forces, apply to a universe on the brink of collapse? At its core, string theory seeks to bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that don't always play nicely together. In a contracting universe where gravity becomes overwhelmingly dominant and quantum effects are magnified, this unification becomes crucial. String theory suggests that particles like electrons, quarks, and even photons are not just dots in space but one-dimensional strings whose vibrations determine their properties. In a shrinking cosmos, these strings could behave in entirely new ways, potentially reshaping our understanding of matter, energy, and even space-time itself. One of the most intriguing possibilities is that string theory could prevent the universe from collapsing into a singularity. As space shrinks and energy densities skyrocket, the behavior of these tiny strings might create a kind of quantum repulsion, counteracting gravity's pull. Imagine the universe as a rubber band being stretched to its limit. String theory suggests that at a certain point, the rubber band might snap back, triggering a rebound rather than a total collapse. This idea ties into the concept of the Big Bounce, where the universe cycles through endless phases of expansion and contraction, never truly ending but always transforming. But string theory's implications go even further. In a collapsing universe, the extra dimensions proposed by string theory, often thought of as hidden or curled up, might become more pronounced. These dimensions, which are usually too small to detect, could uncurl or interact in ways that alter the fabric of reality. For example, the collapse might cause these dimensions to stretch or warp, creating new pathways for energy and matter to escape the crunch. This could mean that the universe doesn't end in a fiery singularity, but instead transitions into a new state, perhaps even giving rise to a fresh Big Bang. String theory also offers a potential explanation for the behavior of black holes in a contracting cosmos. As galaxies merge and black holes grow larger, string theory predicts that these gravitational giants could dissolve into fundamental strings, releasing their energy back into the universe. This process, known as black hole evaporation, could slow the collapse or even create pockets of stability where the laws of physics remain intact. It's a scenario that transforms black holes from cosmic devourers into cosmic recyclers, reshaping the universe's final act in unexpected ways. Yet, for all its elegance, string theory remains a work in progress. While it offers tantalizing possibilities, it's still largely theoretical, with many of its predictions untested. The extreme conditions of a contracting universe push the boundaries of our understanding, leaving us with more questions than answers. But that's what makes string theory so compelling. It challenges us to think beyond the limits of our current knowledge and imagine a cosmos that's far more dynamic and interconnected than we ever realized. As we explore the role of string theory in a contracting universe, we're reminded that the story of the cosmos is far from simple. From the tiniest vibrating strings to the largest structures in existence, every piece of the puzzle matters, shaping the universe's ultimate fate. Whether string theory provides a path to understanding the collapse, prevents a singularity, or introduces entirely new phenomena, its story is a testament to the endless creativity and mystery of the cosmos. And as we continue to probe these ideas, we're reminded that the journey to uncover the secrets of the universe is as awe-inspiring as the destination itself. As the universe contracts, pulling galaxies, stars, and even the fabric of space-time inward, there's an even more profound question to consider: what happens to consciousness itself? For beings living in a collapsing cosmos, the very nature of thought, perception, and awareness could undergo dramatic changes. How does consciousness, something so deeply tied to the structure of the brain and the physical world, adapt to a reality where space is shrinking, time is warping, and the fundamental laws of physics are breaking down? Let's explore what the collapse of the universe might mean for the minds that inhabit it. At its core, consciousness arises from the complex interactions of neurons in the brain, a delicate dance of electrical and chemical signals. But in a contracting universe, the environment that sustains these processes could become increasingly hostile. As gravity's pull intensifies, the physical structures of brains, or any hypothetical consciousness-bearing systems, could face immense strain. Picture a brain being compressed under the weight of a collapsing cosmos. Neurons, the building blocks of thought, might no longer function as they should, disrupting the flow of information that gives rise to consciousness. In this scenario, the very essence of thought and perception could be distorted or even extinguished entirely. But the challenges to consciousness go beyond the physical. Time itself, a fundamental aspect of our experience, could behave in unpredictable ways as the universe contracts. In our current expanding cosmos, time flows forward, creating a clear distinction between past, present, and future. But in a collapsing universe, time might slow down, stop, or even reverse, as suggested by some theories. Imagine a mind trying to make sense of a world where cause and effect are no longer clear, where memories of the future might be as vivid as memories of the past. Such a reality would challenge not just how we think, but how we perceive existence itself. For beings in a contracting universe, the experience of consciousness could become fragmented or surreal. As space-time warps and the laws of physics falter, the senses might deliver conflicting or distorted information. Imagine seeing light shift from red to blue as wavelengths compress, or hearing sounds that stretch and distort as time slows. The familiar rhythms of life, waking, sleeping, dreaming, could be thrown into chaos, leaving consciousness adrift in a sea of disorienting sensations. In such a world, maintaining a coherent sense of self might become an impossible task. Yet, there's another possibility: consciousness might adapt. If life exists in a collapsing universe, it could evolve new ways of processing information, creating minds that thrive in conditions we can barely imagine. These beings might perceive time and space in ways that are utterly alien to us, finding order in what we see as chaos. Their consciousness could be shaped by the unique rhythms of a contracting cosmos, allowing them to navigate a reality where the rules are constantly shifting. It's a reminder that consciousness, for all its fragility, is remarkably resilient, a product of evolution that can adapt to even the most extreme environments. What makes this exploration so fascinating is its blend of science and philosophy. The collapse of consciousness forces us to confront questions about the nature of existence. What does it mean to be aware in a universe that's unraveling? How do we define thought and perception when the very fabric of reality is in flux? These questions push the boundaries of our understanding, inviting us to think beyond the limits of our current knowledge and imagine a cosmos that's far more complex and far more mysterious than we ever realized. As we consider the fate of consciousness in a contracting universe, we're reminded of just how interconnected the cosmos truly is. From the tiniest neurons to the largest galaxies, every piece of the puzzle matters, shaping the universe's ultimate destiny. And while the idea of a collapsing cosmos might seem like the end of everything, it's also a reminder that the story of existence is far from over. Whether consciousness adapts, transforms, or fades away, its journey is a testament to the endless creativity and wonder of the universe, a story that continues to unfold even in the face of collapse. The idea of a contracting universe is both humbling and exhilarating, a concept that forces us to confront the fragility of existence while marveling at the sheer complexity of the cosmos. From the fiery collapse of the Big Crunch to the unpredictable ripples of quantum fluctuations, we've journeyed through the mind-bending theories that attempt to explain what might happen when the universe decides to reverse its course. Each theory offers a unique perspective, from the dramatic implosion of galaxies to the subtle interplay of forces like dark energy and gravity, painting a picture of a cosmos that's far more dynamic than we often imagine. While the ultimate fate of the universe remains shrouded in mystery, one thing is certain: the questions it raises are as profound as the answers are elusive. Will the universe collapse into a singularity, or could quantum mechanics offer a way out? Could we witness the birth of a new cosmos, or are we destined for an eternal cold void? These possibilities don't just challenge our understanding of physics, they invite us to rethink our place in the grand tapestry of existence. The universe, after all, isn't just a collection of stars and galaxies. It's a story, one that's still being written. What's truly remarkable is how these theories, while speculative, push the boundaries of human curiosity and creativity. They remind us that the universe is a place of endless wonder, where even the most extreme scenarios can spark new ideas and discoveries. Whether the cosmos ends in a crunch, a bounce, or something entirely unexpected, the journey to uncover its secrets is as awe-inspiring as the destination itself. So, what do you think will happen when the universe contracts? Will it be the end of everything or the start of something entirely new? Share your thoughts in the comments below. We'd love to hear your ideas and theories. And if you've enjoyed this deep dive into the mysteries of space, don't forget to subscribe for more explorations of the cosmos. The universe is full of questions, and together we'll